Okay, so now it's 12 o'clock. I think we can start the seminar. So hello and welcome to the first ICMAB Online Seminar. My name is Anna Mai, and I'm the Head of Communication and Outreach of the Institute of Material Science of Barcelona, the ICMAB. And I'm very glad to welcome you here to this online seminar entitled Magnetism Fights for Health, a quantitative lab-on-chip rapid diagnostic test for malaria. So by Riccardo Bertacco, full professor at the physics department of the Politecnico di Milano. Thank you, Riccardo, for accepting to give this seminar online instead of coming to the ICMAB as it was planned. Before introducing you the host and the speaker, I would like to let you know to all the attendees that during the seminar and at the end of the seminar, you can ask questions through the questions and answer icon that you have in the bottom of your screen. So you can write there the questions that you might have. And after the seminar, Josep Fontcuberta, who is the host, will read the questions to the speaker. If there is some issues with this, we can also unmute you if you raise your hand, which is also an option you have in this platform. Okay, so now I will pass the virtual floor to Josep Fontcuberta, who is the host of this seminar. He's from the Laboratory of Multifunctional Thin Films and Complex Structures, and he is the one who invited Riccardo, so I let him introduce you the speaker. So thank you all, and let's start this seminar. Thanks.
Okay, good morning to everybody. It's a kind of experience to have this first seminar via internet with all of you. And it's a big pleasure to have as a first speaker Riccardo Bertacco, a friend from Politecnico of Milano and a great expert in magnetism, but in something else that you are going to learn today. Riccardo, he did a PhD on physics in Milano after a master in electronic engineering, and I mention that because you are going to see that he's able to combine some fundamental understanding with final functioning and a lot of stuff in electronics and making devices that is quite uncommon. I think you are going to learn quite a lot from him. So he did a PhD in physics, and then he moved for a while to CNRS Thalès lab in Paris, working in the lab of Albert Ferret on spintronics. And later on, he went back to Milano and managed to be a full professor there on physics at the physics department at the Politecnico of Milano. So Riccardo, he started his scientific career using electron microscopist, and then mixing this knowledge with surface magnetism. So you see that it's a kind of uncommon, I would say, it's a kind of uncommon career, somebody starting from electron microscopy and then moving to surface magnetism. So that means that he's able to combine a different knowledge, trying to solve problems, and he combined this knowledge nowadays, integrating this knowledge into spintronics, combining with nanoelectronics, and with applications in biology, as you're going to see. Riccardo is the leader of the nanomagnetism for biology and spintronics at Politecnico Milano, and he's also the director of what is called the Polyfab, which is a fab for nanofabrication and microfabrication of electronic devices. So he's able to integrate the basic knowledge into final device and final products. He's also the responsible director of a joint research lab with ST Microelectronics, which illustrates again this effort to combine basic understanding with final products. So today, Riccardo is going to present, as the title of his lecture says, some insights of what can be done using spintronics to solve critical health issues in the world. Better known nowadays than coronavirus, which is malaria, that for years it has been killed on millions of people in the world, and we need to find a way to solve or to address this very difficult problem. Thank Riccardo for accepting to be here, and we are going to listen to you with much attention, trying to learn as much as possible. Thank you, Riccardo.
Thank you very much, Pep, for your kind introduction, and thank you for inviting me to deliver this seminar. It's really unusual also to me to give a speech like this on the web, but we are used to give lectures in this period using similar platforms, so I'll try to do my best. Obviously, when you invited me, I was supposed to come to Barcelona, and we were discussing before, I was supposed to walk on the Ramblas, which is not what we can do in these days, but let's try to do our best also to keep, I'll say, our work more or less in the same direction that we chose before the virus itself. Okay, today what I'd like to do is to tell you a story. I'll try to tell you a story that could be inspiring for some of you, possibly, but it's a story strongly connected to my life, to the evolution of my career, but also of my life. What you can see in this first slide is just a picture of a river in Africa. The name of the river is Sanaga, and it's a river close to a small village in which I've been living for 2 years when I was younger, say immediately after graduation. And it will be a story in which, as I am showing here, it will start exactly from this experience. So in this seminar, I will try to start with the basic concept about malaria diagnostics and TMek, which is the name of the device and that we developed. We'll move to the physical properties of the hemozoin crystal that we are using as biomarkers, and which is the strong connection with magnetism that I will explain later on. And then I will show you how the development of TMek has been, I'll say, my relevant activity during the last 2 years. I will show you the state of the art, and I will also discuss the social mission which is connected to the development of this project. Okay, let's start from the very beginning. In this slide, you can see here the location of Mbalmayo, which is the name of this village, is in Cameroon. It is very close to the capital Yaoundé. It's 30 minutes by car from the airport of Milan. And this is a picture taken many years ago when I was there with my wife, Valeria. You can see here me and my wife with our students and the other teacher in a school which was a school of arts, Institut de Formación Artistique at that time. And okay, immediately after graduation, me and my wife, we moved to Mbalmayo for 2 years, volunteers. At that period, we made direct experience of malaria. I got malaria at least twice during my stay in Cameroon. And here you can see another picture, which is a picture in which you can see me and 3 PhD students, Marco, Francesca, and Lorenzo. And this is a picture taken 1 year ago when we were in Mbalmayo for the pre-validation of our test for malaria diagnostics, which is TMek. So what's the origin of TMek? The origin is t-RBC. t-RBC is the name of malaria in Ewondo, which is the local language of the village in which we have been living for a while, say 25 years ago. And now the question is, what is connecting now of the story of 25 years ago and the actual story? It's something that happened just by serendipity. One day, more or less 3 years ago, I was reading some papers. I came across a paper that was discussing the magnetic properties of some crystal produced by plasmodium, and this crystal can be found in the infected red blood cell in the fibroid. The name is hemozoin, and this turned my attention towards malaria again. So, you know, it's a sort of association which happens sometimes. It was very, very simple. I am a professor of magnetism in Politecnico. I've got malaria, so my thought was, okay, if malaria is magnetic, that's probably my job. I have to spend some time in this direction. And this was the origin of the story. So the origin of the story was a call by a program called Polysocial Award by Politecnico Milano, in which they gave some grant to project with some social mission. We applied, we got some money just to start to see if the idea was a good idea or not. And this was exactly the beginning of the story. This is how it works. Here you see our team, which is an interdisciplinary team that you can see here. And essentially is made of me, Giorgio Ferrari, who is another professor of Politecnico di Milano, which is also who is responsible for the electronics that we are using, and Professor Gianfranco Beniamino Fiore, who is the responsible for the hematite treatment, is a biomedical engineer. And here you see the 3 PhD students I mentioned before. And now Luca Paroni, who is another engineer who joined us in order to push further the development of our technology toward the exploitation. And what about the partners that we have, say, in our work? I would like to mention especially Ospedale Luigi Sacco, who is now really working hard on the coronavirus, because they are with reference pool in the north of Italy for the test on the coronavirus, and especially Professor Spinello Antinori, Dr. Romualdo Grande from Divisione Terte Malattie Infettive of the University of Milano. But the other partners are the partners from the hospital in which we have been working for 2 weeks last year in Cameroon, Hôpital Saint-Luc de Mbalmayo, and the ONG COE, which is the ONG who is really hosting, this hospital, who is handling this hospital and started this activity in Cameroon. So interdisciplinary group, many partners, other partners are joining us in this work, but now let's go directly to the beginning of the problem, which is the numbers of malaria. As Pep was mentioning, it's not something which is negligible. It's a problem affecting 3.5 billion people who are still at risk of malaria nowadays. 220 million cases in 2017 and 435 deaths. And when you compare the number of deaths that we are now seeing by coronavirus, we are still below this number, which means that malaria is not something negligible at all. It's really a problem affecting people with serious problems, not only because you have such a large number of deaths, but also for the socio-economical impact on the economy and in the life of these countries. And now what's about the disease? Probably you know that this is a disease which is based on a parasite whose name is plasmodium. There are different species. I'll say the most dangerous one and the widely encountered, especially in Africa, is Plasmodium falciparum, but there is also Vivax, Malaria oval, and another one which is less diffused. But after the mosquito bite, what happens is that there is a first phase of the life cycle, which happens in the liver, and then immediately after, I'll say, this phase, there are these particles, this corpuscle called merozoites, which are now delivered in the free blood circulation. They attack the red blood cells, and inside the red blood cells, they feed on hemoglobin, and they transform hemoglobin into this strange and very interesting hemozoin crystal that you can see here. There are crystals with the brick-like shape. You see the typical dimension is this one, so typically it's on the order of, I'll say, 600, 500, 700 nanometer length, and you see also the size in the order of the section is on the order of 200, 100 nanometers. And interestingly enough, as we will see, these crystals are magnetic. Now, as you see, there is an evolution inside the red blood cell. There is the first phase, which is the ring phase. You see the characteristic ring shape here, the trophozoite, the schizont, and during this evolution, the quantity of hemozoin increases in the red blood cell. When you reach the schizont stage, the pressure inside the red blood cell is too high. There is the rupture of the cell membrane and the delivery of the other merozoites, which continues, I'll say, the cycle here. This is the asexual phase of the development of the plasmodium. But at the end of the illness, there is also a formation of these corpuscles, which are called gametocytes. There are, I'll say, some sexual, parasites, and they are, I'll say, responsible for the second step of the life cycle inside the body of the mosquito. So, this is more or less, I'll say, the story of malaria disease. Obviously, during this asexual phase of reproduction, so if the quantity of infected red blood cell increases too much, this could be a very serious problem for the health. And obviously, you can also reach the state of death for the patient. Now, what about now the problem in terms of sensitivity required for a diagnostics test? I'll say the numbers are listed here. Essentially, we have in our blood 5 million red blood cells per microliter of blood, okay, with typical hematocrit of 40%. Now, in principle, you have to detect 100 infected red blood cells per microliter, which means really, say, 10 over 5 million is not something which is negligible. It's really like finding a needle in the haystack. So you need something which is really sophisticated technology in order to distinguish the single infected red blood cell. And now, what are the current technology used in order to do that? Historically, I'll say the first one, which has been, I'll say, the gold standard for really 100 years. Now things are moving, but okay, it's that direct microscopic parasite investigation, which means that you take a blood smear on a glass slide, and there is a microscopy that an expert guide. We're supposed now to go through, I'll say, and search in this smear in order to find out the infected red blood cell, if he is able to recognize the specific, okay, shape of the infected red blood cell. Now, the typical limit of detection is in the order of, say, 10 parasites per microliter, but only in case of a very expert microscopist using a very good microscope. And the operational time is in the order of 30 minutes, 60 minutes, and the problem is that it's a strongly user-dependent technique. Nowadays, there are some techniques of artificial intelligence in order to replace, say, the microscopist with an algorithm capable to detect, say, the parasite. But still, you need a very good microscope in order to be able to distinguish the parasites. And say here you see in the middle, so the emerging, say, technology which is based on rapid diagnostic test. I'll say emerging, but in the sense that it's widely used. I'll say it has been strongly pushed by the World Health Organization, and they are based on antigen detection. It's a lateral flow device. It's quite inexpensive. And what are now I'll say the problem of this rapid diagnostic test? The problem are related to the fact that the limit of detection is not fantastic. It's just 200 parasites per microliter, and you would like to reach 110. The operational time is 20 minutes. They are rapid, more rapid than the gold standard, but they suffer from a sizable number of false positive and false negative results due to the fact that you're detecting the antigens. And they are not quantitative. They are not quantitative because the appearance of a line here, it just says that, okay, there is the trace of the antigen corresponding to the parasite, but you don't know exactly which is the quantity, which could be a problem because you cannot evaluate the illness stage of the infection. And now, I'll say, last but not least, PCR, especially in the LAMP version, which is an isothermal version, is really the kind of method which is also used for coronavirus. I'll say is polymerase chain reactions, the amplification of DNA sequences, which are typical of the plasmodium. And it's very good test in terms of sensitivity and specificity, but the operational time is long. It's not a cheap method, it's a high-cost method, and it's not quantitative. In order to be quantitative, you have to go through real-time PCR, which is not implemented in this kind of technique. And don't forget that also the cost of this reader is in the order of 3,000 euro, which is not something which is negligible. So this is more or less the scenario. And in this scenario, we try to use also something which is not only peculiar to us, which is the use of the hemozoin crystal as biomarker. There are other tests, and in fact, I came across some paper discussing this test using hemozoin as biomarkers, especially using optical methods. So say it's a sort of magneto-optical method in which you use an external field in order to align the nanocrystal, and then you measure the transmission of light or the reflection of light. In any case, some modulation of the light properties when they interact with the nanocrystal. Okay, now, in any case, everything is based on the hemozoin properties, which is, I'll say, the fact that these hemozoin crystals are magnetic. What's the reason for this magnetism? The reason is quite simple. This is the structure of the typical dimer, which is the basic building block of the hemozoin. And what is happening is that you have the porphyrin-like structure here with an iron here at the center. And typically, the hemoglobin, the oxidation state is 2+. Which is not high spin states. In this case, the magnetic moment is 0. But when you oxidize it, you turn it into the iron-3+ oxidation state in which the spin is 5½ This is a high spin configuration, and that's why you get paramagnetic behavior. And if you have something which is paramagnetic, obviously that's the basic building block for the possibility of manipulating this kind of crystal. And this is really the basis also for the diagnostic method employed so far. Now, which is the entity of the magnet? It is just a tiny susceptibility, it's very, very small value. Here you see in this big picture the evolution from the ring to the trophozoite, skeleton, and finally gametocyte stage for different species, falciparum vivax, malaria, and endovale. And you see that there is an increase of the the volume also occupied by the hemozoin. And in the gametocytes, half of the volume is occupied by hemozoin nanocrystal. But what's the impact in terms of the volume susceptibility for the infected red blood cell? So from literature, you can easily find that healthy red blood cells have a difference of susceptibility with respect to the medium, which is essentially 0, okay? This means that there is no way to attract them because the attracting force will be proportional to the difference of the susceptibility of the corpuscle with respect to the medium. But what happens when you are dealing with an infected red blood cell in the ring stage? You see that the delta key is in the order of 0.8, 10 to the -6. It's a very low susceptibility, but still there. When you move to the skeleton stage, which is that immediately before the rupture of the cell membrane, is 1.8, 10 to the -6. And if you completely oxidize and you turn the hemoglobin into methemoglobin, which is something that we are using also in our I'll say, development for having some, I'll say, a red blood cell which mimic the infected one that we can produce in the laboratory, you get 3.9 by 10 to the -6. Now, what about hemozoin crystal? The hemozoin crystal have a susceptibility of 410 to the -6, which means 410 to the -4. And for the gametocytes, you get 200. So it's not a big, I'll say, magnetic moment that you can typically achieve in this kind of particle, but still enough to allow for the magnetophoretic separation. And now we start with the idea. The idea was this one. As I told you, when I came across these papers, I realized that, okay, I'm a teacher of magnetism, and I'm also director of Polyfab, which is a clean room in which we produce some microchip. So why we do not produce a microchip in which we have some magnetic concentrator, these gray bars here, that can really produce a very strong gradient of a magnetic field under the action of an external field produced by some permanent magnet. And this gradient here will be used in order to do what? By exploiting the competition between gravity and magnetism, the idea was that of attracting now the infected red blood cells corresponding to this pink particles here and free hemozoin towards what? Towards some electrodes placed close to the concentrator, with the idea of using, in this case, just an electrical detection method in order to minimize also the cost and the complexity of the reading apparatus. That was the idea. So the idea to exploit just the magnetostatic separation using the competition between magnetism and gravity without microfluidics in a very, very simple system. And now, I'll say this was the idea, but the first step was, let's try to verify if the physical properties of hemozoin crystals can be really suitable for this kind of concept. And the main problem was connected to the electrical property, but also to the magnetic properties. Why electrical property? Because if you want to detect now some particles using some interdigitated electrode, you have to find that the conductance of your particle must be very, very different from that of the medium. So what about now the electrical properties? Was not so clear in literature, so we tried with some experiments. This is a DC experiment in which we just put some nanocrystal of hemozoin on top of a gold-plated silicon substrate, and by using the AFM tip with a conductive tip, we measure now the current flowing from top here toward the substrate in case of an hemozoin crystal. And as you can see, we found that in a range between -5 and +5 volt, there is no current in the limit of sensitivity of our amplifier. While in the case of the gold, you see that we are saturating the 10 nanoamps, which are really the saturation value of our amplifier. So the good news was that, okay, hemozoin crystal behave as insulating particle in DC, but this is not enough, because when we have to work in the typical situation in which you have some electrodes immersed in a fluid, you have to think about the real situation, which is this one. So essentially, in this case, the equivalent circuits when the electrodes are exposed to a medium is this one. You have a double layer capacitance forming at the surface of the electrode due to ion separation and accumulation here, which is a very relevant capacitance. And then you have the electrode capacitance, which is the physical and geometrical capacitance between the electrodes. And then you have the resistance of the solution of the real medium. Which means that in the end of the day, if you look at the impedance as a function of the frequency in this typical impedimeter detection scheme, you find out that there is an initial part which is dominated by the double layer capacitance, and another one dominated by the capacitance of the electrode. But you are interested in this intermediate region in which it's really the solution resistance which plays the major role. And you have to work here at about, I'll say, 1 megahertz or something like that. In this region, you can exploit now Maxwell theory for the conductance or suspension of particles, and you discover that due to the accumulation of some particle between, I'll say, the electrodes in this region, you will observe a percentage change of the resistance that will be proportional to what? To the volume of the particle divided by the probing volume of the electrode. So you have a linear relationship here between the change in the resistance and, I'll say, the volume occupied. That's the way you can count particles. But, okay, coming back to the properties, the problem was what happens about what happens at the conductivity or resistivity of the hemozoin particles at 1 megahertz. In order to do that, we made some experiments in which we dispensate some different concentration of hemozoin crystals on top of some interdigitated electrode that you can see here, and working in the plateau now of the conductance corresponding to this region here, we were able to detect what an increase of the resistance, which makes, okay, it's a good solution, because we find that also at 1 megahertz, hemozoin crystals are resistive enough to be distinguishable from the medium. And for the infractive red blood cell, there is no problem, because for cells, well known that they are really insulating up to the gigahertz, which means that 1 megahertz is good enough. What about magnetism? There was a strong, a debate at that time on the behavior, because in some paper you found paramagnetic behavior, in another paper super paramagnetic behavior. Okay, we made the measurements and we put now the suspension in the DSM, we measure and you see this straight line which tell you that, okay, it's a paramagnetic behavior, no trace of super paramagnetism. And in this case we were using some synthetic nanocrystal made by Invivogen of the synthetic form of hemozoin crystal which is called beta-hematine, and the susceptibility was in agreement with literature in the order of 4 × 10⁻⁴. And in this experiment, we tried also to compare the magnetically assisted sedimentation of the hemozoin crystal. Here you see the normalized resistance variation as a function of time during magnetically assisted sedimentation on the electrode. And you see that the blue curve is strongly delayed with respect to the red curve, which corresponds to super paramagnetic beats. And as here the susceptibility, magnetic susceptibility is around 1, it's clear that here the susceptibility must be much lower than 1, and it's compatible with this 4 × 10⁻⁴. So they are not super paramagnetic, but okay, even though say they are not super paramagnetic, the magnetism is strong enough to allow for the separation. And so we started with the engineering of the platform for using now this idea of an external magnet and some concentrator to separate these particles, these corpuscles. This was the strategy. We decided to use some nickel post as magnetic concentrator in the field produced by some external magnet. Now the idea is to use a combination of an external macroscopic gradient which is able to attract or delay a little bit the sedimentation of the particles, and then use some concentrator in order to really concentrate the particles at the place where we are supposed to place our detector, which corresponds to our electrode. And this is the idea, just to show you what happens in a simulation made by using COMSOL. You see exactly this story of the concentration on the nickel post. But in order to magnetize the nickel post, we have to use now an assembly of permanent magnet. We are using neodymium iron boron permanent magnet in this configuration in which we have 2 north poles facing each other. In this way, you have a very, very strong gradient produced here. If you just calculate now which is the entity of the gradient of h², which is needed in order to find a magnetic force which is capable to counteract the gravity and buoyancy force here, you immediately discover that you need a very strong gradient of h², which is in the order of 2 × 10⁻13 m² divided by meter cube for a hemozoin crystal, and 9 × 10⁻14 m² divided by meter cube for infected red blood cells. So not negligible field are needed. But okay, with this configuration, we solve the problem. Now what about fabrication? So we are using typical clean-room fabrication. So we typically embed our nickel concentrator in silicon microchip by drilling some holes, by reactive ion etching, and by filling them by electroplating here. At the end, we planize the chip and we deposit some silicon dioxide to separate now the magnetic layer from the electrode. Here you see that's the critical problem for us was the electroplating, but we solved it, and you see some steps in the filling of these holes and the silicon. And finally, you see that we fabricate some gold electrodes directly on top of the nickel concentrator with this annular shape, which is that fitting, I'll say, the round shape of our concentrators. Okay, what about now the experiments? It's not so easy to work with malaria-infected red blood cells, especially in Milano, because we don't have such a large number of malaria cases here in Milano. So we use this model for the infected red blood cell, which is based on the transformation of hemoglobin into metahemoglobin. As it is summarized here, the susceptibility, relative susceptibility of red blood cell treated with this compound, which is a strongly oxidized compound, this sodium nitrite compound, this leads to a susceptibility which is 3.9 × 10⁻⁶, which is not too far from that of the schizont infected red blood cell, which is 1.8. In this way, we were able to characterize our magnetophoretic platform and also our detection platform. So this was the first experiment that we carried out in this configuration in order to check the capability to attract infected red blood cell. Here you see the assembly of the two magnets. Then we place this assembly directly in contact to the rear part, the rear face of our chip, which is placed face down with a nickel micropillar exposed now to the blood sample, which is contained in this cell defined by this gasket in green and the glass slide. The glass slide was used in order to directly observe now the motion of the particle using an inverted microscope and by staining the cells with some fluorescent molecules in order to directly see them. Here you see the typical configuration of red blood cell, treated red blood cell, say magnetic red blood cell, attracted by the nickel micropillars, and this is just a zoom. In this way, we were able to follow over time the capture of the particle and estimate now the capture efficiency, which was defined like this, is the number of treated red blood cells which are captured, which are seen when you focus here exactly, which means that at the surface of the nickel micropillar divided by the total number of particles in the field of view, those placed here and those placed at the bottom here of the cell, which means at the surface of the glass slide. And in this way, we did, I'll say, sort of optimization. Just to make a long story short, the first thing was the validation of the bovine model. And in order to do that, here you see two experiments in black and red corresponding to the bovine model and the human model. Say, in this case, we took some red blood cell from a bovine blood sample and from a human blood sample. We treated them and we created now a model of infected blood. And we measure now the capture efficiency over time. And you see the two curves are superposed within the limits of the error bar, which means that the bovine model was really a good model to be used in order to simplify also all the procedure connected to the treatment of human sample for which you need a sort of ethical committee approval. So it's not so easy to work with a human blood sample. So we have been working with bovine blood samples, and we optimize the geometry of our chip. Essentially, we choose a HCP, hexagonal closed pack configuration, and we have been playing with the diameter of the pillars and the distance, and also with, I'll say, the height of the cell. Essentially, just to make a long story short, we decided to work with this configuration, which is that corresponding to the green curve, which means 40 micron diameter and 160 micron lattice parameter of our HCP lattice. And the reason is that there are other configurations which are better, like this one, the blue one, which corresponds to 40 micron diameter, the distance of 80, but the wiring then of the electrode will become, I'll say, too complex when you have to think that we have to put on top also the electrode. So we decided to work with this one. And in the end of the day, we moved toward the real experiments, which was the real sample preparation we are looking for, which is a very simple dilution of the whole blood in PBS, which means we take a blood sample, we dilute 1 to 10 in PBS, and then we check what is happening. In these experiments, we are measuring the capture efficiency as a function of time in case of whole blood sample diluted in PBS after spiking of some treated red blood cell in order to mimic a real malaria-infected blood sample. And what you observe is that you are really able, also in this case, which is really that representing the real situation, to capture something with a good capture efficiency around 80%. And there is a big difference in between the sample with treated red blood cell and the sample without, I'll say, treated red blood cell, at least up to 10 minutes. Okay, that's okay. We move towards the integrated capture and detection. And this is the layout of the chip that we have been using at the very beginning. As you see here, there is a red area and the blue area. What's the difference between these two areas? The difference is that in the red area, we have the nickel pillars with some electrodes placed above the nickel pillars in such a way that we attract and detect in the reference area, which is the blue one, we just have the electrode without the magnetic concentration, which means that it's a differential measurement in order to suppress the fluctuation that we carry out. So essentially what happens is that depicted here. So we have the measurement electrode here, we have the reference electrode, we apply a positive, we apply two signal which are out of phase. You see plus VA and minus VA here, in order to have what? In case of perfect balance between these two resistors, the measurement and the reference, we have a zero current flowing into the virtual ground of this transimpedance amplifier, no signal. But when a particle is captured here, there will be what? An increase in the resistance here. If the resistance increases because you have an insulating particle, there will be a net current that will enter this virtual ground and some auto signal that will be generated. But in this mode, you suppress a little bit the common mode fluctuation. And what is interesting, what I would like to remind you is that this signal will be proportional to the number of particles, because it depends on volumetric fraction. If you have the same volume, you are counting the particle. And this is the first realization of our apparatus for measuring now the concentration of infected red blood cell. It's a cartridge in which we insert now the microchip, then we close this lid and we create the cell due to the fact that there is a gasket here, PDMS gasket, which is placed on top of this glass slide. And you see the spring contact, which ensure now the electrical connection from the chip and the electronic units here. And this is the without apparatus, in which we have also the assembly of the magnets and the motor for approaching the chip with the magnet. This is just an image of the electronics that we have developed here in Politecnico with the lock-in amplifier and software. Now, what about the real configuration? So far, we have been discussing about a horizontal configuration in which, in principle, we were supposed to use a direct competition between magnetic force pointing upwards and gravity pointing downwards. But in practice, we realized that the best configuration is a vertical one. And it's a vertical one because for the horizontal configuration, you can easily capture a particle only if the height of the cell is very, very small, around 40, 50 microns. But in order to have a larger volume of blood, we decided to work with 500 micron height of the well, and we work in the vertical configuration. This way, what happened? So the particles are sedimenting, are flowing down due to the gravity, but during this motion, they are captured now. They are attracted by the external gradient and by the, say, the local gradient generated by the nickel post. And in this way, we can separate particles and also measure them. And this is just a summary on the field produced by our magnetic arrangement. And this is our protocol for measurement. So we apply the magnet, we approach the magnet, there is a first capture, the current decreases because the impedance is increasing, up to 300 seconds, and a bit more. At this moment, we take out the magnet. The reason is that this initial decrease of the signal is also superposed to some drift that you can't really control. But at this moment, it's like a trigger. So you disengage the magnet, there is a sudden release of the particle. They are no more attracted, they start falling down again. And so there is a signal increase here. You measure this amplitude in this way, and this amplitude will be proportional to the concentration of the particle that you are targeting. And this is a simulation made by computer that shows the trajectory. You see that initially they follow this oblique trajectory. They are attracted by the external gradient till they reach, I'll say, more or less the surface of the chip. They feel now the local gradient. They are attracted now towards the electrode. And in this way, we're able also to simulate the change of the impedance, which is due by the capture, due to the capture by the electrodes, and finally, which is producing, I'll say, the change in the resistance of, which is seen by the electronics. And this is how it works in practice. It's just a video showing you what happens when the operator is loading now the chip. This was done originally also by the personnel of the hospital. Now you can load the sample here in the glass slide. You close the cover, you create your connection, you insert it into the reader. Okay, which is the cartridge, which is inserted, and then the experiment starts, and you see the decrease now of the current, and you will see the difference between an healthy patient here and a malaria-affected patient. So when you, I'll say, release the particle, you see this typical increase of the signal, and this is the amplitude that will be proportional to the concentration. This is the way how it works in practice. And now, what about sample preparation? As I told you, it's quite simple. We just take 8 microliter of whole blood, we dilute in heparin PBS, we create the sample, 80 microliter. We take now 70 microliter, and the fact that we're using heparin and PBS creates a nice solution in which you don't have coagulation and rouleau formation, which is obviously what you need. You want to keep the integrity of each particle in order to attract it and measure it. And this is just the first measurement we carried out on a patient affected by malaria at Sacco Hospital. You see the characteristic line shape that we have seen. That was the first experiment, February 2019, showing that it was working also on humans, not only on models. And at Sacco Hospital, we obviously made some control experiments on healthy donors, showing that in this case, there are no jumps. You see that when you move the magnet, there is no signal change here. And a very relevant experiment corresponding to this one, in which we tried to use now TMek as a tool in order to follow now the evolution of the illness after treatment. This is the case of a patient arriving with virus infection and a parasitemia about 1%. The parasitemia is the percentage of infected red blood cell over the total amount of red blood cell. So you see that we found a relevant signal about 1.2 microamps. What happens 24 hours after? It turns out that the signal decreases, and after 2 days, the signal is almost zero, which is a clear demonstration that we can use the quantitative capability, quantification capabilities of TMek in order to follow the evolution of the illness stage. And this is a difference with respect to the rapid diagnostic test. So we have something which can be really quantitative. How much is it quantitative? It can be seen from these experiments. This is an experiment carried out using a blood sample from an healthy patient. So we took out some red blood cells. We treated them in order to obtain some red blood cell with methemoglobin, mimicking now infected red blood cell. And we measure now the signal amplitude as a function of the concentration of treated red blood cells. And as you can see, we found a signal trend which is almost linear from 100 treated red blood cell per microliter up to 10 to 5, which means that we have, I'll say, at least 3 decades in which we can use quantitatively our test, because you see there is a linear correlation here. And limit of detection in this case was just 100 treated red blood cells, which means 100 parasites per microliter in terms of malaria wards. But okay, if you want to increase now the sensitivity or decrease the limit of detection, we can just increase the capture time from 5 minutes to 10 minutes. And you see that we can now reach the 10 parasites per microliter, which is not negligible at all, because it is like the best limit of detection in hemoscopic analysis, 20 times better than currently used rapid diagnostic test based on antigen detection. And it's really in the order of magnitude of what is looked for also by big agencies like World Health Organization or FINE. That's good news. Now, the other story is, can we also measure free hemozoin? Yes, we can do that. And the beauty of the story is that in this case, also the horizontal configuration works. So that in the horizontal configuration, we are only sensitive to hemozoin. Now we try with a similar calibration curve, but in this case, the limit of detection in terms of parasite per microliter is 5,000. It's much higher than in case of, say, the detection in infected red blood cells. And the reason is very simple. We are really efficient in capturing hemozoin, but they are extremely small, which means the volumetric fraction will be small, the signal is small. At a given moment, you will encounter what the limit of detection, which is due by, I'll say, the noise of your system. So just to tell you, which is, I'll say, the final, the final achievement was this first pre-validation in Cameroon. So we took a flight. We went to Cameroon. This is a picture from the first seminar given to explain to the doctors how it worked. So we see the installation of the apparatus in a small room, 38 degrees temperature, 80% humidity, so the real on-field condition. And this is exactly the instruction and the first learning by the operators who really were handling now the test. This is the first demonstration that he was working on a small child last year. And then we started with the, I'll say, statistical analysis of the performances in terms of the diagnostic test. So you have typically to refer to two indexes. The first one is sensitivity, the other one is specificity. And sensitivity measures how often the test correctly generates a positive results. So essentially, sensitivity is high, according to this formula, if you don't have false negative, which means that you're really able to diagnose something which corresponds to a patient who has got malaria. And specificity instead measures the test ability to correctly generate a negative result for healthy patient, which means that this will be very high if you don't have false positive here. So what happens? So in our case, so we just had the possibility to test a limited number of people. It was just a first pre-validation. And essentially, we had two ways for measuring it. The first one was starting from a venous sampling. Venous sampling is typical way of taking a venous blood sample in our hospital. The second one was a capillary sampling. So for the venous sampling, we had, I'll say, a number of tests that correspond to 75, and sensitivity was 100%. No false negative, that's relatively important, I'll say very important one. And the specificity is about 17%. So we still have some false positive. So if we move now to the capillary, which means we just take a small blood sample from the finger of the patient, we found that, okay, the number here is very, very limited in terms of samples, just 10, but sensitivity is 100%, specificity very high. The confidence intervals are very, very wide due to the low number of samples, but very promising. And I'll say the difference probably is due to the fact that this is really a synchronous experiment. We just immediately take the sample and we immediately measure it without assisting to any deterioration of the red blood cell due to this interval between the sample and the analysis. And what is also interesting is that our performances are very comparable to well-established rapid diagnostic tests. So this is really promising story. So I will skip this one. So just to tell you that after our pre-validation, what we can say is that really TMek can be a direct and automatic quantification method for the parasitemia. It's really something feasible also according to our test made in Sacco Hospital. The quantification circulating malaria pigment is possible. What is interesting is plasmodium test, because we have tested on falciparum and also on vivax. That's very interesting for future development. It's suitable for post-treatment monitoring of the illness evolution, which means that you can follow now what happens during the treatment, as in case of the patient affected by a vivax. We just use 8 microliter of whole blood. Test operating time is 5–10 minutes. And the storage condition for the tests are not really demanding because we are not using reagents at all. And sensitivity is really promising. And also specificity is promising and can be improved if we move to the finger prick. Just a few words and then I will stop. There is an IP protection based on these patents here. And there is an interesting formula that we invented, which is that of the social patent. Due to the, I'll say, social impact of what we are doing, we decided to give up all the inventors the royalties, so we have no rights to receive any any money, so no money from the royalties in case of exploitation of our patents, and we also force our institution to reinvest possible revenues from IP exploitation in social projects. Because what we're trying to implement is sort of a business model based on principle of corporate ethics. So this is something that is now moving on. There are some initiatives in this direction, and this is the conclusion of my talk. I'll say this is what we have done. So this is sort of summary on the summary slide of what we have done, and just to give you with some references here, you can find this tmekdiagnostic.com, some references to our work, and also the possibility, if you want, to contribute also to the development of this test by using a sort of crowdfunding that we have set up. And with this, I'd like to thank you for your attention, and I'm available for questions if there are any questions. Thank you very much.
Okay, thanks, thanks Riccardo for this lecture, in which I think that you have illustrated clearly that one can go from basic understanding of electric measurements to go to basic and fundamental magnetism and to make something very useful, no? So you have used a kind of Archimedes force, but not of gravitational origin, but of magnetic origin, which is quite amazing, no? So anyway, maybe people have questions from your talk. I'm not sure that how to handle that. I should go to the questions probably. Let me try to. There is one comment saying that really amazing and inspiring work. So nice to hear about this story today. Thanks for your initiative. How long does it take for the moment a mosquito infects a person to the moment these hemozoin crystals are formed big enough for the analysis? This is one question. The second is that, is the blood sample use only diluted blood in PBS, or it is needed to pretreat the blood to have a high concentration of RBCs? Third question from the same attendant is that, is the number of malaria cases in bovine population similar to the number of cases on human population? And finally, that MD says that I believe you can reuse your platform for several analyses. Briefly, how do you wash it before use? Ricardo, could you comment on these questions, please? Was I clear enough?
Yeah, definitely. I can also read the questions. So
oh, thank you.
That's a good option offered by the Zoom, which means that there is no difficulty, I'll say, in
thank you.
Question. Okay, let's start from the very beginning. Thank you for, I'll say, your interest in our technology. So the time required for the development of the sizable quantity of the hemozoin strongly depends on the malaria species, but typically, so it takes a few days, okay? A few days now, which means, I'll say it could be 4 or 5 days, something like that. But what is interesting enough is that now if I move back, sorry, I have to move back to the beginning of my presentation just to show you the story. I'll say what we know is that the quantity of the hemozoin is very different in the different stages, but also in the ring stage, which corresponds to the early stage of the infection, we are able to attract the ring infected red blood cell and to detect them. We checked this possibility in other experiments that I didn't show, made in collaboration with Istituto Superiore di Sanità, in which we typically selected now the stage of the infection, and already in the ring stage we are able to capture. Okay, they were a little bit surprised because usually you are not able to separate infected red blood cell in the ring stage, but our system is well engineered, and we can we can capture also the ring. So this means that after, I'll say, when the infection starts, we have some corpuscle inside that we are able to capture. In this sense, I'll say it's quite efficient, the system. Coming to the second question, so about the sample preparation. Yes, I'll say it's only the whole blood diluted in heparin and PPS. No additional treatment pre-concentration is required. So the initial idea of the story was to minimize the sample preparation procedure so that the concentration is carried out in the chip, is exactly at the surface of the chip. So we just take the blood sample from the finger, we dilute in PBS, and that's all. It's ready for the operation. This is a typical operation that is also done in our test. It was done in Africa, I'll say, in the hospital by the personnel, local personnel, and just takes, I'll say, you a few minutes. You don't need a centrifuge or something like that. It's very simple. And the other question is about the number of malaria cases in the bovine population. Okay, this is not exactly what we have done. We didn't use some malaria-infected bovine samples, but we just used some bovine blood sample in order to take out some red blood cell, treat with this oxidizing agent in order to transform hemoglobin into methemoglobin. In this way, we have some red blood cell which have a susceptibility which is similar to that of infected red blood cells. So this is the way we have been using the bovine model. So we are not using really a sample of a bovine infected by malaria, but we are taking out some red blood cell. We treat them in order to have some red blood cell which mimic now the infected one. And coming to the last question was, can we use our platform? Yes. This is exactly what we did, because the chip can be reused many times. It's very easy to do that, because just upon exposure to deionized water, or I'll say if you have deionized water, or in any case I'll say just distilled water, you immediately destroy the cell membrane of red blood cell, so you can easily wash the surface of the chip. Then we use some disinfection using some alcohol solution, and the chip was reused at least 100 times. That's not a big issue. The problem is that you can do that during a trial, but you cannot do that in practice, because for real exploitation you have to work with something which is disposable, because obviously there are some safety issues related to the fact that you're treating some human blood sample. You don't know exactly which are the problems connected to the sample, so it's a little bit critical to clean I'll say the chip and reuse it. But in any case, it can be done. It's something that we are now discussing, because there is a trade-off between the complexity of this treatment and, I'll say, the cost of the chip.
We have another question, and is, what is the typical crystal size and the shape distribution of the sample that you are measuring, on how it affects the measurement and how it varies among patients? Could you comment on that, Riccardo?
Yeah, yes, probably I have a slide here that was, yeah, this slide here, okay. Probably you can see here some crystal, okay, corresponding to different species also of the plasmodium. I'll say, depending now on the species, also the size of the crystal changes a little bit. And this creates some problems, especially for quantification, okay? When you have to quantify if the shape and the size is different, this will create some difficulties. This is more or less inherent to the problem itself. But what we understand right now is that if you move, now let me try to, okay, this is a good slide, sorry. if you move now to the, I'll say, to the different stage, for instance, okay, also in the different stage, you will have different level of accumulation of the nanocrystal. What is interesting is that our platform is somehow capable to distinguish between, I'll say, the different stages in which we have different amount of the crystal, because okay, you can follow a little bit the time evolution of your signal. Anyway, this story of the different size and distribution is something that must be tackled, because if you want to be quantitative, sooner or later you have to face with this different distribution. But if you typically work in Africa, for instance, as in Africa you typically have falciparum, this means that, I'll say, 90% of the cases correspond to a well-known distribution, and in this case, obviously, it's easier.
Okay, and we have another question. Somebody says, thank you for this fantastic talk. And he's asking again, or she's asking again, for what is the typical size of these hemozoin crystals? Maybe this is connected to the previous answer, I guess, no?
Yeah, I'll say the typical size probably can be better appreciated in, let me look, just you can see here, okay, this is the scale bar, this is 1 micron, so the typical length could be, depending on the species, from, I'll say, 500 nanometer to 1 micron, something like that.
There's another question saying that, thank you for your excellent and inspirational talk. I read a paper that says that coronavirus infection could affect hemoglobin in a similar way than plasmodium does in malaria. In theory, they have not proved experimentally yet. Do you think your methodology would be useful, or have thought about it?
Okay, I've no idea about the answer to this question. It's a very complex question. So I also know that people is using chloroquine in these days to treat also people affected by coronavirus. So probably there's some connection, there's some transformation, and what is seen in malaria is also present in other diseases. But I'll say it's too early to me to give an answer to this question. Anyway, thank you for this, I'll say, for this question, because it's also a stimulus to try to better, I'll say, investigate this possible connection.
Okay, we'll have maybe a last question that is related to the clustering of these magnetic crystals that you have. Does it affect to the measurement itself?
Okay, I'll say clustering could happen in the blood, but in any case, some clustering will happen at the surface of our chip when we attract now the hemozoin crystal and we detect them. I'll say it's not a big issue for detection, okay, because when they accumulate on top of the electrodes, okay, they just occupy the volume and it's enough for us. If some clustering happens in the blood, it's not a big issue again, because they are just forming a particle which will be bigger, but with the bigger magnetic moment, so we can attract it, there is no problem. The real problem of clustering is something that could happen at the level of the infected red blood cells. So if it happens that for some reason there is a clustering of red blood cells, that's a big issue, because you can have a cluster in which just one of the cells is infected and the other one are not infected. And this creates a big issue, because obviously the gravity force will increase, but not the magnetic one. So we won't be able to attract it. For this reason, our protocol of sample preparation must really keep the separation and integrity of each infected red blood cell in order to avoid this clustering, the formation of rouleau that could be really detrimental for the capability of attracting and quantifying now the red blood cells.
Okay, there is a new question that maybe should be probably the last one, otherwise we are going to be out of schedule. And the last question is that, is there a way for instance, chemical treatment to take out hemozoin crystals out of RBC? If so, it would perhaps possible to use similar equipment, but with electrochemical measurements, reduction of oxidation of iron, which would be quantitative. Did you comment, Riccardo?
Yeah, I'll say there are two answers to this question. I'll say we already have a way to distinguish free hemozoin crystal from infected red blood cell containing hemozoin crystal. And the way we can do that is just using the horizontal configuration or the vertical one. Because in the vertical configuration, we can capture both hemozoin crystal and infected red blood cell. But in the horizontal one, we are only able to capture hemozoin crystal. So just using, I'll say, this different configuration, right now, we can distinguish the signal coming from infected red blood cell and hemozoin crystal and only hemozoin crystal. But what is suggested is probably a possible evolution of the story, because right now we are just using small voltages applied to our electrodes on the order of 100 millivolts in order to avoid electrochemical reaction, and just use an impetimetric detection in which we are just measuring some volume of insulating material occupying now the space between the electrodes. Moving towards a sort of electrochemical measurements could be interesting in terms of the possibility of adding new information and possibly the capability of better distinguishing things. But that's a possible evolution of the story. So thank you for this suggestion.
Okay, so maybe before closing, I would like just to make a question from my side as well. I mean, I think that one of the targets it would be to increase sensitivity and to avoid, and the second objective will be to avoid, to improve accuracy or to avoid false positive or false negative, no? So regarding the first question, to increase sensitivity, probably you need to increase the force that you have on your magnetic object. So to optimize the geometry, to increase, to get a larger force, I saw that you explore distances between your pillars, magnetic pillars, you explore the distance between them, and also the diameter. But the force, I guess, is dictated just by the edge, no? But the edge of your cylinder, of your pillar, the edge is what determines the force, because the gradient is there. So if you make it taller or shorter, the gradient is going to be basically the same. So the only way, well, the only way, I don't know, but a way that I do see is to increase the density of pillars. Is there any limit to that? So increase the density of edges, let's say, because that will get you a larger force. This is one question. And regarding the false positive, which is the physical reason? Why do you detect something which is magnetic and is not a plasmodium? Well, a plasmodium, magnetic crystal that comes from the malaria itself.
Okay, let's start with the first question concerning, I'll say, the density of the pillars. You are definitely right, Pep. And as I show you probably, I didn't comment too much on this point, but it was in this slide. So we try with different densities, okay? Sorry, because now my screen is a little bit difficult to read. I don't see exactly the screen itself. Okay, let me remove a little bit. Okay, now it's clear. If you look here, you see that, for instance, with 40 micron height of the gasket, the blue curve displays a much higher capture efficiency than the green one. Sorry, because now I need this. Okay, the blue curve displays a larger efficiency, and the blue curve corresponds, as a matter of fact, to a density which is higher, because the distance is 80 micron. What's the difficulty associated to this layout? The difficulty is due to the fact that the wiring now for creating on top of each of these nickel post some electrodes will, I'll say, will become more difficult. It's really a problem of, I'll say, minimization in some terms of the numbers of electrodes that you put on top. Because don't forget that the sensitivity in the end, I'll say, in terms of detection, you want to have what? You want to have a large volumetric fraction, which means the volume of captured particle divided by the probing volume of the electrode must be high. So if you increase too much the number of electrodes, obviously you are increasing the denominator of your fraction and you lose the signal. So there is a trade-off between the two things, let's say the capture efficiency and the detection efficiency. That's why we choose this solution, which corresponds to the green curve, which is, I'll say, very similar to the blue one, and it makes easier the detection.
Okay.
That's the first answer. The second one was connected to the reason for the false positive.
Yeah.
I'll say we know that if there is a transformation of hemoglobin into meta-hemoglobin, the red blood cell starts becoming magnetic. And which is not something which doesn't happen in our body, because there is an aging process that leads to the formation of some meta-hemoglobin also in our red blood cells. So what does it mean? It means typically that in case of sampling happening, for instance, in the morning, and the analysis which is carried out, I'll say, early in the evening, so there is a time in which this deterioration can take place. And I'll say my guess is that in our first trial, as we were not in condition to really oblige the clinicians to be synchronous, I'll say sampling and immediate, I'll say, analysis, we had a very long delay time on the order of, I'll say, 10 hours, 15 hours, and that could be a big issue. But interestingly enough, when we move to the prick samples, we use this sampling from the capillary region, and in that time, the delay time was reduced to 3 hours, and in that case, we didn't find false positives. So our hope is that moving towards, I'll say, this prick sampling, so we could be able to better see a situation, which is the physiological situation in the blood sample, without alteration due to the delay time between sampling and analysis. That's my guess and my hope. Even though there are a lot of experiments to be carried out, also on patients affected by other hematic illness, like thalassemia or other things, in order to better understand which is the distribution of red blood cells which could play an anomalous magnetic behavior. And this is not something well, I'll say, investigated also in literature.
Okay, I'm taking the very last question before the end, because otherwise it's going to be too last. The very last question is that there is a question saying that the production of hemozoin is unique to malaria plasmodium, or other infections also produce these crystals in the red blood cell. Do you know? Could you comment on that, Riccardo?
I'll say there are other transformation which could produce, I'll say, some hemozoin. I'll say in humans, I'll say there are some, I'll say, some limited cases, but for instance, there is another disease which is schistosomiasis, in which it's well known that, especially in the eggs, there is an accumulation of hemozoin crystals. So what I'd like to say is that probably, I'll say, it shouldn't be so easy to find hemozoin in a human blood sample due to other illness state. But we know that hemozoin is not unique to malaria. It's also found in other situations. And that could be also interesting for future development and application of the technology.
Okay, so we end up the meeting here. I should thank you, Riccardo, for your great talk. It has been very inspiring as some attendees already mentioned. I should also thank Anna May for her effort to build this conference and the people from the IT office in our institute for making that possible, and to all of you for attending this meeting. Thanks to all of you and have a nice day.
Thank you very much, and thank you for your attention.
Bye-bye.
Thank you. And thank you also, Pep, for inviting Riccardo and making this seminar possible. Thank you to all of you, and see you in our next online seminar.
Thank
Goodbye.
you. Bye-bye.